Okay, Cacus AB, for day 5. This is a good review assignment for our upcoming test. There's still a couple more things I'm going to cover, and some of those things might be on this assignment that we haven't covered yet, so that's fine. So wait to do those until we've covered them, and then you can go back and do them. So here's a function. Find the slope in secant for x equals 2 and x equals 3. Okay, so the slope of a secant line is like when you have a curve and you take 2 points and you find the slope like that. That's the secant line. So we're not going to use derivatives here. We're going to say, okay, well, the slope of the secant line between these points is going to be rise over run. So it's going to be the y value from x equals 3 and 2 and over the difference in the x values, rise over run. Now, you could do it the other way. You could do F2 minus F3 as long as you do 2 minus 3 on the bottom, as long as you're consistent. So F3 would be 27 minus 6 is 21. F2 would be 8 minus 4 is 4. 3 minus 2 equals 17 over 1 is 17. So this is good work to show, set up to get partial credit. If you make some minor mistake plugging the wrong number in, at least if you wrote this, I would know that you had the right idea and you just made little minor details. It's also a good point on for response questions on the actual AP test. Here I'm giving you a point, F2. I'm giving you the derivative, then the y-intercept of the tangent line to y equals f of x at x equals 2. This is the x value, right? This is the y value. So the y-intercept of the tangent line. Well, we should probably find the tangent line first, which we have everything we need. Y minus 6 equals negative 3 x minus 2. So that's the tangent line. It probably would be helpful to change this to slope-intercept form because we have to do some other work with it. So that's our slope-intercept form. In fact, the y-intercept is super easy to identify here, right? So, otherwise, usually the way we find the y-intercept is we set the other variable equal to 0, and that gives you the y-intercept, right? So, okay, slope of the tangent line. Now, tangent line means we're actually taking the actual derivative, right? So tangent is tangent to that. So we need to take the derivative using the power rule, 3x squared minus 2, and then plug 3 into it. So that's going to be 3 times 9 is 27, minus 2 is 25, is the slope of the tangent line. Okay, different than find the slope of the secant line. Okay, all right, the next problem, this looks like a definition of derivative problem, and I want you to do it the long way, okay? And you're gonna have one like this on your test, so you got to really show that it's all about the work. I've also purposely made this slightly not the actual derivative, so even if you try to use a derivative rule, it will give you the right answer. So don't try and fake it. But we're going to say equals the limit, and you should write the limit on each step. If we plugged in 0 right now, we would get 0 over 0. And so essentially the way we've been trying to get past that indeterminate form, one way, the very first way, was to factor the whole out, and that's the technique we're going to take here. So this is the function, and we're going to plug x plus h into it wherever we see an x. So that's going to be 3 over 2 minus parentheses x plus h. I'd put those parentheses. Guarantee people will make mistakes if they don't. Minus 3 over 2 minus x minus h, all over h. We did one like this on one of the recent worksheets, I think the assignment 4 worksheet. Now, we're going to want to combine these together in the least common denominator. We're going to want to combine this all together. This I'm going to think of h over 1 and just multiply it. So this is 3 over 2 minus x minus h minus 3 over 2 minus x plus h. And then I'm going to multiply by h over 1 instead of dividing by h. We need to combine these together. So we have to give them least common denominators. And even though they look very close to the same, they are not the same. And so we have to multiply one by the other. Whatever you do at the bottom, you do at the top. Right? So this one we have to multiply by 2 minus x plus h, top and bottom. And so then what we're going to get next is you have to distribute that. That's going to be 6 minus 3x plus 3h minus, now when you distribute this 3, distribute the negative in with it at the same time if you want. That saves a little bit of work. So that's going to be minus 6 plus 3x plus 3h all over. There's an h, and then there's a 2 minus x minus h, and a 2 minus x plus h. Don't multiply the bottom out because that's already nicely factored and everything. The top we gotta simplify and combine like terms and stuff. Now, the whole point of this is to factor this h out. We know the h is where the hole is. And the only way you're going to factor h out of everything on top is if all the terms have h's. So all the terms that don't have h's really should cancel out at this point. If they don't, you know something's wrong. So now we have 6h. And so now we've finally gotten here to where the h's cancel out. That's the hole in the graph. And then we're going to plug h equals 0 in to any h's that are still here, those h's. So you're going to get 2 minus x, 2 minus x. And so that could be your answer. Your answer could be 6 over 2 minus x squared if you want. That could be your answer. Anyways, like I said, this isn't quite the derivative there. One minor thing is there should be a 2 under this because this is that symmetric difference quotient. But I'm looking for you to do it the long way on the test, one of them. And you guys should be writing limit every time. Show your work. You're going to have some graphical limits, of course, which should be quick and easy, but be careful not to make little mistakes. Most of these, I think, are intended to line up with nice values. Okay, so f of 5 is 3. That's just the value of the function. The limit as x approaches 5 would be two-sided limit, and both sides have to agree, and it looks like they're both going towards 2. They have to agree. If they don't agree, it does not exist. As we approach 2, they're both going to negative infinity, right? But we're going to say does not exist. I think on my solutions, I may have had negative infinity. We're going to say does not exist. So no negative infinity. If it's a one-side limit, yeah, I want infinity or positive or negative infinity. As we approach 8, they're both going to 0, right? They're both from both sides approaching 0. This is the slope. So make sure you catch those little f primes. As we approach 2 from the right side is positive infinity. Now, this is the kind I want infinity on. A lot of people are going to say negative infinity. Well, that's what the y value is doing, but the slope is a positive, super steep slope. It's super steep, but it's a positive slope. Left, right, it's going up on the right side of 2. Okay, as we approach 8, we're going to say does not exist because the two sides do not agree. Very clearly, one's negative, one's positive, so they don't agree. But even the numbers are probably different. Values of x where the absolute value of f of x is not differentiable. Now, maybe we should sketch that graph. Absolute value would flip the negative parts up, right? And then the positive parts would stay where they are. Not differentiable means not continuous. So any jumps or holes or vertical asymptotes are going to be on that list. So, we could put those on there. 2, 5, 6. And those actually wouldn't be differentiable on the original graph. But in addition, not differentiable means not smooth. So even if it is continuous, but it has a sharp corner like at 1, 3, and 8, those are not differentiable. Okay? Values of x naught for which the value of the limit of as x goes to x naught f of x does not exist. So where does the limit not exist? Well, at 2 and 6. It exists at holes and jumps. If both sides agree, it exists at corners. So there you go. Those are all those answers. So those are going to be quick, but they're going to add up to a good chunk of points. And then you're going to have a big chunk of problems asking you to do algebraic limits. And some of these I'm going to ask you to do L'Hopital's rule in addition to not using L'Hopital's rule. Sometimes you just plug the number in to -8 and gives you a nice number, and it's a continuous function, and it's as simple as that. Or a constant is going to stay 5 no matter what x is. Those are super quick and easy. 7, if I plug negative a in, I get negative a cubed plus a cubed over negative a plus a, which gives you 0 over 0. So I'm probably going to have you do this problem 2 ways. One, factor it. Factor out the whole. So this is a sum of cubes, so it's going to be x plus a, x squared, ax in the middle, same, opposite, always positive, over x plus a. There's the whole, cancels out. We're going to then plug negative a back in here, and we get positive a squared, positive a squared, positive a squared. You get 3a squared, right? And I'm going to have you do it with L'Hopital's rule. So we got the 0 over 0. So we're going to take the limit as x approaches negative a of the derivative of the top, which would be 3x squared. Now, a is just a number, so it drops out. Derivative of the bottom is 1, the a drops out. Plug negative a in here, guess what you get? 3a squared, positive, because the negative gets squared and made positive. So I'm going to want you to do it both ways, and they should both agree with each other. I mean, that's going to be a good check, I guess. Here we're plugging 2 in. We're going to get 10 minus 10 on top, 0 over 0. So I'm going to have you do it 2 ways. I'm going to have you factor the whole out, and then I'm going to have you do L'Hopital's. So to factor the whole out, it's cubic, so we're going to want to use long synthetic division. We don't need rational root theorem because we already know that the x minus 2 is what we hope to factor out. And so the 2 is a root. 1, 0, 1, negative 10. Drop the first number, multiply by 2, add those, multiply by 2, add those, multiply by 2, add those. You should get a 0 at the end, unless you've made a mistake. So what this gives us is it gives us the limit as x approaches 2 of x minus 2 is the thing we just factored out, and this is what's left after factor out, x squared plus 2x plus 5 over x minus 2. That's the whole, and we plug 2 back in, we get 4 plus 9 is 13. Now, we're also going to do it with L'Hopital's rule. So it's going to equal the limit as x approaches 2 of the derivative of the top, 3x squared plus 1 over the derivative of the bottom, 1. So that's going to be 13. Same answer. That was kind of easy. That was kind of nice. After this chapter, I'm going to let you do it however you want, but I'm going to make sure you know how to do it both ways this chapter. Now we're approaching 3 from the left-hand side, which is going to give you 6 over 0. It's not negative 3. It's positive 3, but from the left side. Now, is this 0 a positive 0 or negative 0? Because our answer is going to be some kind of infinity. Technically does not exist, but I want you to write the infinity. So it's like we're plugging something in just to the left of 3, which would be like 2.9999 here. Up here, it doesn't really matter. It's pretty much 6. And this is pretty much 0, but it's negative. Okay. Number 10, we're going to plug 5 in. We're going to get 25 over 0. Similar thing. We know we're going to get some kind of infinity. Plugging in something to the right of 5, so like 5.0001, for instance, as just a rough idea, which makes this negative. So now it's negative infinity. Next one, we're going to infinity, which gives you infinity over infinity. Okay, which means we could do L'Hopital's rule, and I might ask you to, but you really usually wouldn't on these. You want to look for dominant terms. And so the 3x cubed is dominant on top, the 5x to the fourth is dominant on the bottom, and then this guy dominates that guy. The bottom is getting way bigger than the top, so it's going to go to 0. Otherwise, we could do L'Hopital's rule. And you'll see that on these in behavior problems, it's usually just not a great idea. The dominant terms is way faster. So we take derivative of the top, 9x squared over 2 plus 20x cubed, and we would get infinity over infinity again. So then we would have to do it again. We have to take the limit as x approaches infinity of 18x over 60x squared, and we would get infinity over infinity again. So we'd have to do it again. And we would get 18 over 120x. At this point, we're like, oh, that is clearly going, that's 18 over infinity. That's 0. So I don't know if I'll have you do it on those ones, but I mean, you know that it is a possibility. Okay, number 12, we're going to negative infinity. So let's see, negative to the fourth power is positive, square root is positive. So it's some kind of positive infinity on the bottom, on the top. On the bottom, the negative gets squared, but then there's a negative, so it's going to be negative infinity. So we know we should get a negative answer, right? We know we should get a negative answer. And this is the dominant term, and this is the dominant term, which would be square root of a times x squared, right? And they have the same degree, right? And so if we plug it in, now here's the deal. A lot of times we put those absolute values around it. Here we don't really need it because even if x is negative, it gets forced to be positive here again. So it's going to actually work that the answer is the square root of a over negative d, or negative square root of a over d. Usually put the negative in the top or in front for final answers. Okay? So you can do L'Hopital's, but that involves some rules we haven't really talked about. So I'm not going to ask you to do that. This is infinity. This is a cube root. It's going to go to, this is going to be, negative infinity on the top. You can take cube roots of negative numbers. That's the dominant term. This is the dominant term at the bottom. It's going to be a positive infinity. So we should get a negative answer. And these are the dominant terms. So that's going to be negative cube root of 2 times x. We don't do absolute values on these ones with the odd roots. This is going to be, you can take the cube root of 8 out, and then there'd be still a cube root of 2 left. So it's going to be this over, it's going to be negative cube root of 2 over 2 cube root of 2. So it's going to be negative 1/2. Okay. Okay, next one. If we plug 0 in, tangent is sine over cosine, right? And so we're going to get sine 0 over cosine 0 is 1. 0 over 1 is 0, and on the bottom we get 0. So we can't factor the whole out of this one because it just doesn't work. We could do L'Hopital's rule, but probably not going to ask you to do that on this one. I want to use that other little trick where we memorized that sine of x over x is x goes to 0 is 1. But you got to show that pattern. You got to force that pattern to happen. So here, I'm going to have the sine 3x on the top, and then the cosine 3x separate. And then we have another 1 over sine 2x. So I'm spacing everything out, okay? This guy doesn't matter. It's going to go to 1. Don't do anything extra here. Here we need a 3x. Here we need a 2x. The x is the 1x, the one new x on the top and one new x on the bottom balance each other out. There's a new 2 on the top though that needs to be balanced out, and a new 3 on the bottom that needs to be balanced out. That goes to 1. That goes to 1. Your answer is 3/2. This is the work I want you to show. Okay. Next one is piecewise function. So usually the work I want to see on this is that you're considering both sides as we approach 2 on the left. It's going to be approaching 2 on the left of, I guess, that x squared minus 9, which is going to give you -5. And we're going to take the limit as x approaches 2 from the right. And it happens to also be x squared minus 9. So this is kind of a weird scenario. And they're both -5, so the answer is going to be -5. They both have to agree. Okay, these next problems, I don't want you to do these the long way like we did on the first page. I want you to be like, oh, hey, this is a derivative of something. And I don't want you to do L'Hopital's rule and all that stuff. I mean, you can make this a lot of work like we did on the front. I want you to say, okay, well, what's the function that we're taking the derivative of? Well, I think it's a 1/2 x to the third. You see it here and you see it here. Now there's 4s where the x's are. We'll deal with that later. Now, what's the derivative of that? Just using rules, 3/2 x squared, right? And now we're going to plug 4 into it for our final answer. If there were just x's there, this would be the final answer with the x's in it. So it's going to be 3/2 times 16, which is going to be 24. Okay, next one, same thing. You should be like, hey, this is the definition of the derivative. What's the function we're trying to take the derivative of? Square root of x, which you probably want to think of as x to the 1/2 for the derivative power rule. 1/2 x to the negative 1/2, which is 1/2 square root x, a little nicer. And then we're going to plug 16 into it. And your final answer is going to be 1/8. Okay? So you're definitely going to have some problems like that. Good chunk of problems on your test. Next page. I don't think, I don't know if we've talked about this kind of problem yet, but we're going to have it on, we may have, I don't know, we might. So I want you to sketch a position versus time graph. So one of the things that you need to know about like cars and real life problems is that you can't jump from one speed to another one without going through the speeds in between. So it's got to be a smooth graph. It can't have any sharp points because that would be where the slope goes from one slope to the other just magically. So it says sketch initially at rest. That means the slope should be like 0. Okay, it should be kind of flat. And then accelerates until t1 seconds. So I think something that would be helpful is to go ahead and just extend these lines up because I'm going to want to see defined dots at each of these times. Okay, your graph could look a little different than mine in size and stuff, but it should have the same-ish shape. Now, accelerates means getting faster and faster. The slope of this position versus time graph is velocity. And if it's accelerating, that means velocity is increasing. So, we could say, okay, well, it's starting at a 0 slope and getting steeper and steeper until that time. It says it then maintains its speed until t seconds, which means that the slope is constant speed, no acceleration. Okay, so it's got to be a straight line, but smooth right here. I don't want to see any little corners right here. It then slows down until stopping. So now, as a negative acceleration, slowing down till it gets to a 0. It's got to have a 0 slope here. It's got to be nice and smooth. At t4 seconds, the car returns. So I guess from t3 to t4, it's doing nothing. So that's a flat line because position is staying the same. Its velocity, the slope of this is 0. T4, the car returns in direction, its starting point at an ever increasing speed. So getting steeper and steeper and steeper. With 1/3 of the way home, car sputters to a stop. Okay, so 1/3 of the way home, I would, it depends on how big you made your graph, but 1/3 of the way home remaining, we haven't gone 1/3, we've actually gone 2/3. You got to read that. Let's say 1/3 would be, somewhere around here. So with 1/3 of the home, the car sputters to a stop at T5. So it's getting steeper and steeper and steeper and steeper and steeper, and then it goes to a 0 slope right there. So it's got to bend kind of quickly, decelerates because the car just sputters to a stop. And then graph it, and then it's stopped, right? And nothing else has happened, so that'd be another horizontal chunk right there. So the graph should look something like that, when the graph is speeding up, accelerating. it should be concave up, you know, it's getting faster and faster and faster. And then this is a constant speed. So it means no concavity. Yeah. And then here it's going to slow down. And so the slope's got to get less and less and less steep because the slope of this is your velocity. So it's got to be concave down, you know, and then this is just, it's stopped right here, right? And then stopped right here. And it's just, you know, horizontal because it's not going anywhere, right? And then this should be, you know, concave down. It's speeding up, but in the negative direction. So it's getting steeper and steeper, negative. So, okay, you're gonna have a problem like that on your test. So you're gonna have to kind of sketch it out. Okay, here's motion with gravity, which I think we've talked about before in an earlier unit. Well, no, not motion with gravity, just motion. So, I mean, it might be gravity or might not. Well, yeah. During a flight of a rock thrown upward from the top of the bridge, the altitude reached. So I'm just giving you the altitude. So it is possible you might have to create your own. And so altitude vertical is going to be negative 16t squared plus v naught t plus s naught. Okay, so they're giving you initial velocity. They're giving you initial height, h naught, which is the top of the bridge. Find the altitude after t seconds. Okay, well, two seconds. So we just plug 2 into this. And, you know, 4 times, that's going to be negative 64. This is going to be 256 plus 144. So that's going to be 300, 400. So it's going to be 336 feet. It does have units here, so these answers need units. Okay, find v bar, which is the average velocity. Now, it's not going to be v4 plus v2 divided by 4 divided by 2, like, oh, just like a simple average of these two endpoint velocities. Okay, that you know, and so there's this idea that the average slope of a curve is really just the slope between the endpoints. Okay, so what it's going to be, v average is going to be v4 minus, no, not v4. It's going to be h4 minus h2 over 4 minus 2. So if you have a position graph and you want the average of all, if these slopes, if all these slopes are your velocities and you want the average of all those in between, you're just going to find the average. You're just going to find the velocity between the two endpoints, between the times that you want on your position curve. Because the slopes of the position curve, that's velocity, and we want the average of all these little slopes, and it ends up just being the slope between the two endpoints. So this is your setup. So we're going to plug 4 into that. Maybe we should just find that on the side. 16 times 16, I think it's negative 256 plus 256, 512 plus 144. So that's going to be positive 256. I think that's going to be 400. Okay, that's H4. So this is going to be 400 minus 336 over 4 minus 2. So that's going to be 64 over 2 is 32 feet per second of the units. Okay, find the velocity after 3 seconds. So we got to find the velocity equation, I guess. Should be the derivative of the position equation. So it's going to be negative 32t plus 128. And then we're going to plug 3 into it. And so we get negative 96. So that's going to give you positive 32 feet per second. Okay. And then the maximum height, well, we got to do extreme value theorem. So max height, that means we need h prime equals 0 and to find critical points, right? And so I think, and that ends up being velocity when velocity equals 0. So velocity, we just found in the last problem, was negative 32 t plus 128. So we're going to set that equal to 0, solve for t. 32t equals 128, divide both sides by 32, you get t equals 4. So that's your critical point. We need endpoints, so we need to figure out when from the maximum height of the rock. Okay, so we need to figure out, I guess, when it hits the ground. So let's see. We haven't done that yet, I don't think. So to find when it hits the ground, so we're trying to find endpoints. So 0 is usually an endpoint. And then this would be impact. And so impact is when h equals 0. So we're going to set h equal to 0 and try and find the time that happens. So we can factor hopefully negative 16 out. So that would be 7, 8. I think 8 of those. It'd be negative 8t. And then that'd be another 16 after that. So that'd be negative 9. And then we would factor it t minus 9 plus 1. And so we get t equals 9 and t equals negative 1. Now we're going to throw the negative time out because that's acting like it was at some height before we threw it, like it hit the ground on both sides. So it's always going to give you two answers, the negative 1 or the 0, 1. We'll ignore. So then we're going to make a table of time, and we're going to put those in there, 0, 4, 9. And we're going to plug them into the h equation. Negative 16 t squared plus 128 t plus 144. And I think we've calculated a lot of these. You plug 0 in, you get 144. Plug 9 in, you should get 0. We plugged 4 in already up here. It was 400. So if you already have the work for that, you don't have to redo it. This is your max. This is your min. So we're going to say the maximum height of the rock is 400 feet at time t equals 4 seconds by extreme value theorem. Checking endpoints, critical points. So this is what I want you. This is what I want you to write. This is extreme value theorem. Endpoints and critical points. Units, justification. Okay, so that's what I want for anytime we're trying to find a max or min, absolute max or min. You need the table, critical points, endpoints. Okay, the velocity impact, that's not too hard because we just found it happens at time 4. So we plug that into our velocity equation, negative 32 times 4 plus 128. And we get negative 128 plus 28, which is 0, which actually shouldn't be a surprise. Oh, wait, no. Velocity at 9. So plug 9 in. And it should be negative because it's going down. So this is going to be at 270, negative 288. Plus 128 equals negative 160 feet per second. Should be going down. Should probably going faster than when it started going up because it ends further down. So it's gained more velocity from gravity or whatever. When all the values of t for which the position and velocity have opposite signs. position and velocity have opposite signs. So what would be really good here is to just do some line checks right above and below each other, because then I think that would make it easy. So if we already found position equals 0, right? So velocity, we need to find the. We already found when velocity equals 0 too, right? Right up here, that was time was 4, right? And position would be when the function equals 0, which we already found back when we found -1 and 9. Now I might put this on my line check. So my line check for h is going to have a -1 and a 9. I'm going to test a point like x equals, I'm going to do 0 into h, which would give you a positive, and then a negative, and then a negative. Okay, and then velocity would just be at 4, which would be in between these, and then we could test x equals 0 for that also, and that's going to be positive over here, negative over here. So where do they have opposite signs? Right here, from 4 to 9. Interval notation. You have the same sign from well, you could even say over here, -infinity to -1. They have opposite signs. But we're not going to include negative time for our final answers. Okay. There you go. So you have a problem like this on your test where do some motion stuff, ask you several different questions about that. Okay. So derivative at which of the labeled points is f of x the greatest of the labeled points? Well, I would say at f, it's the greatest. The least, I would say a. So we're checking endpoints and peaks and valleys or just whatever. Where is f prime the greatest? Where's the slope the greatest? Well, the slope, that would be a really steep positive slope. So I'm going with, it's either A or E. So we'll say E, but I mean, the thing about A wouldn't be good because slope is a two-sided issue, and we don't know what's happening on the left side, so it actually might be undefined there. So undefined for now, as long as you don't have two sides, since at end. Okay, slope of the absolute value of the graph greatest. Well, maybe I should sketch it. It would look kind of like that, I guess, like that. I mean, I don't. Where is it the greatest? Well, it's not going to be E anymore because it's negative. It's not going to be D because it's sharp corner. It can't be there. So I'm thinking it's got to be B, right? Slope doesn't exist at corners or cusps, right? Okay. Number 21, find the coefficient of the expansion. So this is really just like trying to have you get practice Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 0, first, second, third, fourth. So this is what we want, fourth power. And so then we're going to write it. There's a -3 in front of everything. I'm going to put everything else in parentheses. So it's going to be 1 times x to the fourth, h to the 0, plus 4 times x to the third, h to the first, plus 6 times x squared, h squared, plus 4 times x to the first, h to the third, plus 1 times x to the 0, h to the fourth. All right, and then we got to distribute this in to all of these. So this would be 3x to the fourth minus 12x cubed h minus 18x squared h squared minus 12x h cubed minus 3h to the fourth. So we want the coefficient of the x cubed h term. So I guess we didn't have to do all of it. We could have stopped there. The coefficient's just the number in front. Okay. Anyways, a little practice with Pascal's triangle. Okay. Next one, determine if at x equals 2, f of x is continuous, differentiable, both, or neither. So if it's continuous, that means the y values have to equal each other at the connection. So let's just plug 2 in and see what happens. We get 8 and we get 20. And so these aren't equal to each other, so it's definitely not continuous, and therefore it's not differentiable. Okay, so it's going to be neither. Now, that would be the best thing. If you kept going to differentiable, it potentially give you the wrong answer. That's when the slopes are equal. Now, if these did equal, then you would go on to this. But we want to find the derivative of the piecewise graph. So it's going to be 3x squared when x is less than 2, 2x plus 8 when x is greater than 2. And so we plug 2 into that, and that would give us 12 and 12, and you'd be like, they're equal, so they're differentiable. No, because it wasn't continuous. So be careful. All right, 23. We have some problems like this. Is kind of like using an estimation technique to find the slope of a secant line to estimate a derivative. So we're saying, okay, let's use this formula, and we're going to estimate. Okay, and so h equals 0.1, which is the distance between these. So that's like that h that we usually think about in the definition of the derivative. And we want to find the answer for 3. So we're using this guy. So we're going to say, all right, well, f prime of 3 is about the limit as x approaches 0 of f of 3. That's what's going in there, right? Minus f of 3 minus 0.01 over 0.01. That's the exact answer, right? Or no, this is an approximation. We're getting rid of the limit and doing an approximation. Instead of h going 0, we're going to use 0.01. So then from the table, f of 3 is 10. And this would be f of 2.99, which is 6 over 0.01. Gives you 4 over 0.01. You can move the decimals over so you don't have decimals. 1 to you have to multiply by an extra 10 to move the decimal place over. In order to do the bottom, you got to do the top. So this is going to be the same thing as 400. That's your estimate. Okay, so you're using values from the table. You're using the left. This is a left-sided difference quotient, and whatever difference quotient they give you, you're going to use that and pick the right values, plug them in, get the answer. Okay, sketching the derivative graph is something that I think is in a lesson that I haven't showed you yet, so you probably want to wait till you see that lesson, then try this problem. But I'm going to go ahead and go over it now just to have it in this video. So if you're trying to sketch the derivative graph, you want to look for some easy slopes, like 0 slopes, flat spots. So, but that's going to be an open dot because the slope doesn't actually exist at a corner or cusp. So it's going to 0 on the left. It's going to 0 at 0. It's going to 0 at 2. Okay. Then you might look at vertical tangents, because that's going to be a vertical asymptote because the graph is getting infinitely steep. And so this is an infinite positive infinity slope. This is a negative infinity slope. So on this side, it's blowing up, getting closer and closer on the end. And on this side, it's blowing up in the negative direction. And then over here, we might say, okay, that looks like a vertical tangent also. So we're going to have a vertical asymptote here. That's a negative slope. So it's going this way. Okay, and then here, this is a constant slope, down 1 over 1. So the slope is just -1 all the time. Okay, open die here, and it's just a flat slope. So this would be the graph I would want for that derivative graph, but you'll get some more practice on these. Make sure you watch the lesson and do the homework before you try this problem to get the most out of this. All right, it's a good review assignment.